Hi everybody, so today we're continuing notes on section 6.2, except now we're going to be looking at radicals instead of rational exponents. So go ahead and pause and write this down real quick. All right, so let's go through this piece by piece. So first things first, a radical expression is simplified when the radicand, explain that in a second, has no perfect nth powers as factors. And let me actually underline nth, because that's the index. And any denominator has been rationalized. So the part that's underlined in pink, any denominator has been rationalized. That basically just means there's no radical in the denominator. Now the stuff that I underlined in green and blue corresponds to when we're looking at this thing. So the nth powers, that's referring to your index. So if it's a 2, that means you don't have any squared terms. If it's a 3, you don't have any cubed terms. If it's a 4, you don't have anything raised to the 4th power, or perfect 4th terms, etc. And then the oops, that should say radicand. Just turn that L into an N. There we go, radicand. So the A underneath that thing is called the radicand. The radical is this thing, the V shape with the line over it. So radicand is what's underneath. Properties. Really similar idea to other things that we've looked at. So properties, basically, if you have, let's say your power is 2. If you have the square root of a squared, it's just a, because that nth root and the nth power cancel out. If this was the 8th root of a to the 8th, it would equal a, etc. Multiplication. We can separate it out. So if we have something multiplied underneath the radical, we can split it up into 2 separate or 3 separate, so on, however many things there are. You can separate them out and multiply them. Then if they are divided, same idea. If you have the radical with a fraction underneath, you can rewrite it as the radical of the top divided by the radical of the bottom. And last but not least, rationalizing the denominator. I kept this in pink as well to coordinate with the pink that's up here. So if you have a radical in the denominator, what you do is you multiply the top and bottom by the square root of whatever this thing is to do what we call rationalizing. Get rid of the radical on the bottom, because the square root of a times the square root of a, we use the multiplying property, smush them back together. Square root of a times square root of a becomes the square root of a squared, and then that comes out as a. So we'll look at some examples of that. All right. First couple examples. Go ahead and write those down. So first one, the cube root of 135. What we are looking for is perfect cubes. Or in other words, when we draw a little tree, we want to look for a number that happens 3 times. So what I'm going to do here, I have 135. Now this ends in a 5, which means I know 5 goes into it. So if I do 135 divided by 5, I get 27. Now 27 also breaks down. I can draw a little tree from that. This breaks down as 3 times 9. And then 9 also breaks down as 3 times 3. And we just found a group of 3. And then the 5 is the little leftover guy that didn't get used. So when I write my answer for this, a 3 is what comes out of the radical, and then what's left stuck underneath is the cube root of 5. So because this is like saying the square root of 5, the cube root of 5 times 3 times 3 times 3. This is basically what this little tree means. Oops. which is the same as the cube root of 5 times 3 cubed. And we know that when we have the cube root of something cubed, the exponent and the index will cancel each other out, and this number comes out of the radical. I never write this step, but you can if you want to, if you're more comfortable with it. Next one, the index is 5, which means we are looking for groups of 5. I'm going to start with the 243. So 243, first thing I notice, it's not even, which means 2 will not go in. So I'm going to see if 3 goes in. And the fun little trick, add up all the numbers. 2 plus 4 is 6, plus 3 is 9. 3 goes into 9, which means 3 will go into 243. So when I divide that, I get 81 and 3. And then I can still break down 81. First thing I think of is 9 and 9. And then each of those also break down as 3 times 3. Do we have any groups of 5? You should have said yes. We have 5 3s. We have this one up here hanging out, and then all 4 of these down here. And we don't have any leftover numbers that didn't get used because all of these 3s were at the bottom of our little tree branches. All right, now when I do a similar thing for the things with exponents, I'm going to do it a little bit differently just to make it a little more, I don't know, I guess I'll say user-friendly. So for example, for the a to the 8th, I'm going to write this one as a to the 5th. So that takes care of 5 of the 8. And then I'll have 3 more. So 5, 6, 7, 8. And then this a to the 5th, that's a group of 5. And then I'm going to do a similar thing with the b to the 14th. Realize now I should have spaced this out a little bit better. So b to the, that was Lucy's shadow. So b to the 14th. I'm going to write this as b to the 5th. That gives me 5 of them. B to the 5th. Now I have 10 total. B to the 4th. Oh, and I just realized my A's, I forgot to underline what got left over. So for the B's, I have 5 of them. I have 5 of them again. And then I have these 4 that are left over. And lastly, for the C's, I just have 5 already, which is great. I don't have to do anything. All right, so writing my answer. My constants, I circled the 3's, so a 3 comes out, and there were none left over. The A's, I circled the a to the 5th, which means an a will come out, because remember the 5th root of a to the 5th is a. It's the property. That a cubed will be left over on the inside. Then the B's, I have a b to the 5th, so a b will come out, and then the other b to the 5th means a second b will come out. So I'm going to have b squared. And then I have 1c circled. And then I have the 5th root. Everything that I underlined in purple is what gets left behind. So a cubed, b to the 4th. Did not make the cut and get stuck behind. All right, now I'm going to draw a little arrow for these things. The a, that was for taking the 5th root of a to the 5th. The b squared, that's for taking the 5th root of b to the 5th times b to the 5th, etc. All right, let's look at another example. Go ahead and write that down. So this one we have division. First thing I notice is that 5 and 32, I can't simplify that at all. So I'm going to go ahead and just use the properties of radicals and rewrite this as the 5th root of 5 divided by the 5th root of 32. Now 5 is not going to break down into anything else. I'm stuck. It's just going to stay that way. But the 32, now I know looking at this that 2 to the 5th is 32. And you'll kind of start to get the hang of it as you do more of these problems. You'll start to get really good at recognizing numbers that can come out of these things. But let's go ahead and draw our little trees. So 32, I know that 2 goes into it, so it's 2 times 16. And then 16 also breaks down as 4 times 4. And then each of those also break down as 2. And we have 5 of them. Because remember, it's the 5th root, so we're looking for groups of 5. If it was the 7th root, we'd be looking for groups of 7. The 11th root, we'd be looking for groups of 11, etc. So the top I couldn't do anything with. But the bottom, a 2 comes out, and I didn't have any stragglers that get left behind. So that's my answer. All right, let's look at another one. So this is division again. We don't have any like terms that we can go ahead and cancel out now, so I'm going to write this as 2 separate things. So the 4th root of 2m to the 4th divided by the 4th root of n to the 8th. Now, do you notice anything right away on the top that we'll be able to take out of the radical? If you said the m's, you are correct. I have an m to the 4th, which is already a group of 4 because we're looking for groups of 4 based on our index. Now the bottom, I'm going to write this one. So n to the 8th, I know there's an n to the 4th in that, but then there's also another n to the 4th because 4 plus 4 is 8. You really got to remember those properties of exponents, when you can add them, when you multiply them, etc. So on the top, what comes out of the radical on the top? If you said m, you are correct. And then what gets left over that wasn't used is the 2. So the 4th root of 2 gets stuck under there. How are we going to rewrite the bottom? If you said n squared, you are correct. Because you pull out an n from this circled one, and then you also pull out an n from this circled one. All right, next example. We have a cube root divided by a cube root. Now, a cube root of 2 on the bottom, we can't do anything with that one. But the top, what I want you to do right now is pause, try doing a little tree and see if you can find something that will come out, and then push play when you're ready to check. All right, go ahead and check. So this is how I chose to break it down. I used 5 and 50. And then from 50, I did 5 and 10, but you could have also done 25 and 2. Would have been fine as well. So your tree may look a little bit different, but you should have found that you have 3 5s. You have a group of 3, and you have a 2 left over. So when I rewrite this, what comes out of the radical? What's going to be written on the outside of the radical? If you said 5, you are correct, because we had the group of 3, and the index is 3. So I can pull 1 out. And then what's stuck left over is the cube root of 2. But I also have a cube root of 2 on the bottom. So what's my final step before I highlight this as my answer? You should have said cancel out the roots or something along those lines. Because it's the exact same thing on the top and bottom. And the top is multiplied, I want to point out. If the top was addition or subtraction, you absolutely, by no means, can just cross those out. But because the top is multiplied, it's totally fine. So the answer is 5. All right, last 2 examples. We're going to practice rationalizing the denominator a little bit. First example, square root of 12. Is there anything that we can still pull out of the radical? You should have said yes. 12, I can break that down as 4 and 3. 4 is a perfect square. 3 is left over. So I can rewrite this as 2 divided by 2 radical 3. Now I'm going to go ahead and simplify this again and cross out the 2's. So now all I'm left with is 1 over the square root of 3. Now to rationalize this denominator, I need to multiply the top and bottom by this radical. So by the square root of 3. When I do that, the top will become the square root of 3, because 1 times rad 3 is rad 3. And then on the bottom, rad 3 times rad 3 is 3. And remember, that is your property. Rad 3 times rad 3 smushes together and becomes radical 9, and the square root of 9 is 3. Last one. 81 divided by 10 does not simplify, so I'm going to go ahead and write this as 2 separate radicals. So square root of 81 over square root of 10. Do either of those simplify? You should have said yes, the top, and the top becomes 9. So 9 over rad 10. What do I multiply the top and bottom by? If you said the square root of 10 or radical 10, you are correct. So the top is going to become 9 times rad 10. And then rad 10 times rad 10 becomes just 10. Now, does anything simplify further? You should have said no. The 9 over 10 does not simplify. And just in case you're wondering why we can't cross out the radical 10 and the 10, is because the radical 10, that's underneath a radical. The 10 down here, if you were to put that in a radical, it'd be like saying the square root of 100, which is not the same. That's why you can't just cross these out. Alrighty, that's the end of our notes. Have a good rest of your day.